Hello, friends. Welcome to another edition of Math That Matters. It's Friday. It's late. I want to go home. But because I love you so much, I'm going to do this video. I want to make sure that things are, prepared ahead of time well enough that you have a chance to succeed, because you know that myself and Neil and whomever is out here in the cyberspace is for you and not against you, that we're trying to figure out the best way to teach you stuff that we think matters, stuff that we love, and to, bring something of the image of God that we're made in into what we do, into our efforts. And I hope that you can see that really, truly, this course is a labor of love. And we're putting a lot of time and energy and resource and heart and prayer and study into trying to figure out the best way to say things to you all in a clear fashion and in something that will make an impact. So without further ado, this is lesson CT3, Critical Thinking 3. Let me share my screen. And we'll jump right into it. So we're in this section where we're looking at inductive arguments. So arguments based on evidence, not just kind of like philosophy and premises. This isn't necessarily propositional logic anymore, where there's a true or a false, but it's a matter of kind of looking at the evidence and seeing what direction it points and saying, based on the thinking and the evidence and the numbers, what is most likely is. So we're looking for explanations here. And because a lot of these explanations in inductive arguments are probabilistic in nature, I thought you needed to know a little bit about probability. Like, where does that come from? And what are some of the basic principles of probability to govern not just your calculating abilities, but your thinking? There's a woman named Marilyn Vos Savant, the world's smartest woman, so they say. She writes a column for Parade magazine, and people write questions into her that she answers. And here's one of them. It's sort of a decently long article. And the highlights of this article, you can see there's two little kids here, two little boys. So somebody writes in this question: a woman and a man, unrelated, each have two children. At least one of the woman's children is a boy, and the man's older child is a boy. These are two separate families. Do the chances that the woman has two boys equal the chances that the man has two boys? And she just says, well, the probability that the woman has two boys is 1/3. She says about, whereas the probability that the man has two boys is about 1/2. So her answer is no. In this particular case, the readers wrote back, and some of them said, I just can't accept that. The probability the woman has two boys is 1/2, just as it is for the man. And one reader says, I'll send $1,000 to your favorite charity if you can prove me wrong. Well, I wish somebody would take me up on that one. So she decides to answer this cleverly, probably differently than I would choose to answer it. But it's a really interesting thing that she did. She said, I'd like to take a survey. So she put the ball back in her reader's court. And she, knowing statistics, there's a principle in statistics called the law of large numbers. And what it says is that the empirical probabilities will fall in line with the theoretical probabilities as long as the sample size is big enough. So she's just like, hey, let's just go out, let's take a survey. And then you'll see here, she also looks at some Census Bureau results. And the interesting thing is, there's a survey of almost 18,000 respondents. And amongst those respondents, what she predicted would be 33% ended up being 35.9%, which is really close to the 1/3. Then she goes into the census from 1993, shows you how old this article might be. A sample size of like 43,000, which is ginormous. It's amazing. And amongst that sample, the category that she predicted would be 1/3 was about 34%. So at least she had all this evidence to support her claim. And it says the reader who promised to send $1,000 appears to have lost the argument, and it sounds like may have never sent that $1,000 in. So I guess the question is, does that feel right? If you get a whole bunch of numbers, you ask a question and somebody says, I'm just going to go out And I'm going to let the numbers create an argument for me, because if I pull enough numbers, and by the way, these numbers are so large that it's an absolutely convincing argument, even though it might not feel satisfying, because you think in a math class, you don't just go out and look, you figure it out. However, empirical arguments, empirical reasoning, quantitative reasoning actually just goes out and looks at what is and tries to figure out an accurate what is answer, and then says, well, that's my conclusion, which doesn't seem like it satisfies very well, but actually it's pretty effective, especially with a sample size this large. Now, here's how I probably would have answered the question, and maybe it would have satisfied the guy. Maybe it will satisfy you. But she says this: at least one of the woman's children is a boy, and the man's older child is a boy. Do the chances that the man has 2 boys equal the chances that the woman has 2 boys? So this is all I did. She said, at least one of the woman's children is a boy. So I just put like B stands for the situation where the younger one's a boy and the older one's a boy. GB would be the younger one's a girl and then the older one's a boy. I'm just making a little code. And then BG, actually BG is different than GB, isn't it? And every one of you that has a sibling that's older or younger knows that the position in the family does matter. So GB, a girl and then a boy, is not the same thing as a boy and then a girl. Those are totally distinct, different events. So look at this, the probability, considering all possible events here in this particular family, if at least one of the woman's children is a boy, there's one scenario where there's 2 boys out of 3, or 1/3. But if the man's older child has to be a boy, that means it could either be that the older one is a boy and the younger one is a boy, or the older one is a boy and the younger one is a girl. There's only 2 scenarios in the man's case. And so the probability that the man has 2 boys is 1 out of 2. So I think it simplifies a somewhat complex problem and maybe answers the problem more convincingly, but not in as interesting and fun of way as Marilyn did. So I appreciate that. And it was a good illustration of empirical probabilities. So let's talk quickly about empirical versus classical versus subjective probabilities. An empirical probability is simply an experiment or collecting data where we say, how many things did we see in a particular category that we're calling a success? Maybe 2 boys in a family, maybe something else, divided by how many total things were there. And obviously the successes have some counterparts that we might call failures, and successes plus failures would equal trials. Classical probability, or sometimes called theoretical probability, is looking at the possibilities, kind of considering the situation like I did in the previous problem, and looking at the number of ways something could happen divided by the total number of ways anything could happen. So the number of ways some particular event could happen. And that's sort of what we're used to in a math class. But in a statistics class, if we use probability, we can just go out and look for numbers and just calculate a ratio, which is just a percentage of the number of things we observe in a certain category divided by the total possible in whatever it is we're looking at. Subjective probability is really just an educated guess, but we use it all the time. And hopefully it's not just based on a story like we've talked about, but it's based on some evidence or some expertise. But we constantly are doing risk analysis, and we're moving toward or away from certain things that we think are probable or improbable, what's desirable, what's not desirable. And so we're constantly evaluating likelihoods. I'm going to pull out on the road and I'm wondering, is that car that's coming too close? Am I going to pull out in front of that car? Am I going to have an accident? What is the likelihood? And if in my mind I do this calculation of it's not very likely that I have an accident, then I'm probably going to go. Or if I have a really fast car like I have, I might just go anyway. All right, so empirical probability is simply the number of times some event E occurs divided by the total number of observed occurrences. We usually call this the sample space. So if you have a problem and you're like, it's just 383 out of 751 in a particular category, you just divide that, you get 0.51, which is 51%. So basic probability is really pretty simple. But wait, there's more, of course. Of course, we're going to do our ands and our ors and our nots because we're looking at logic situations, and sometimes events aren't as simple as a single event, but they're the conjunction or disjunction or the negation of an event. So that's what we're going to look at today. Ands, ors, and nots with probability. By the way, there is a relationship between probability and statistics. One is sort of like probability is making a prediction of how likely something is to happen. So it's kind of looking forward and wondering what could happen and how likely it will be to happen. And statistics is kind of looking backwards and saying what did happen. But they're actually related because sometimes you can look at what did happen and then you can say, I think what did happen might tell me something about what will happen or how likely what will happen. So you can see there actually sort of is this before and after relationship between probability and statistics. A few words that you're going to need to get comfortable with. So probability is just the chance of an event occurring. And a lot of times we do experiments, probability experiments. So we'll flip a coin or we'll roll a die. We'll pick a card from a deck of cards. So you're going to have to get a little bit familiar with flipping coins and what could happen, heads or tails, or rolling a die, rolling 2 dice. So that's something that sometimes people haven't seen. There's actually 36 different things that can happen, different outcomes, which is the result of a single trial. Like if I flip 2 dice, or I should say roll 2 dice, and I'm going to give one color and the other a different color. So if I have like a red die and a white die, and I get a red 4 and a white 3, that's actually a totally different thing than a red 3 and a white 4, even though they add up to 7. Who said I was looking at the sum? It's a different thing. It's a different outcome. And that set of outcomes is called the sample space. Here we go. Probability experiments. Drawing a marble from a bottle, tossing fair coins. We can bend the coin and make them go toward a heads or a tail, that sort of thing. It is instructive to know that in a deck of cards, there's 52 cards. Of those 52, there are 4 suits, right? Spades, clubs, diamonds, and hearts. And within each suit, there are 13 different, what are those called? Numerations or something? Yeah, the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, the jack, the queen, and the king. So you kind of got to be a little bit familiar with cards for this assignment. Yeah, and so here's just an illustration of the 36 different outcomes when rolling 2 dice. That might be helpful. If you can't picture something in your head, then you can always Google it, right? And find a picture, and then you can count. You could find a picture of the cards in a deck when you're doing the card problems. That might help you. All right, now let's get to some properties of probability. This might be a little tricky for you to read, but I'm so used to reading symbols that to me it just reads like a fast-paced novel or something like that. So P parentheses A is our notation for the probability of event A. And this principle simply says that the probability of an event has to be between 0 and 1 because it's a percentage. So a probability of 1 is a certainty, and a probability of 0 is a certain not, like something will not happen if the probability is 0. We're used to the little tilde, and this visual puts a bar over the A, and that means not. So the probability of not A is 1 minus the probability of A. So if the likelihood of something happening is like 70%, the likelihood of it not happening is 30%. If there's a 70% chance of rain, there's a 30% chance of not raining. 3 doesn't really matter, and 4 doesn't really matter for your purposes. Now we get to our operators here. So, or, this is interesting, the probability of event A or event B is the probability of event A plus the probability of event B minus the probability of A and B, which is kind of interesting. Now, if 2 events don't have an and what that means, if 2 events cannot happen at the same time, they're called mutually exclusive, and we don't have to worry about the probability of A and B because that would be 0. If they can't both happen at the same time, the likelihood of them happening both at the same time is 0. And so, or kind of just means plus, which is nice. The probability of something or something else, you just add them together. But if there is the possibility that they could both happen at once, think about this. The probability of A plus the probability of B would double count the probability of A and B, because A and B would be a part of A. It would also be a part of B. So that's why we have to subtract it off, but we'll practice that a little bit. And our AND operator, the probability of A and B, is actually the probability of A times the probability of B, assuming the events A and B are independent. And what that means is A happening or not happening does not change the probability of B happening or not happening. So that's where we're headed. We'll talk about that a little bit. I just pulled some problems from the assignment. You have a worksheet this time. I didn't think there was enough probability questions in the logic text, so I just got you a worksheet. So here we go. The probability of A or B. This is our union operator. And what I can do is, if the problem gives you numeric values like counts, then I can just take the number of things in A plus the number of things in B divided by the number of things in the sample space, and that just means the total number of things. So if you look at number 9 here, an instructor is selected at random, find the probability of that being a math or a science instructor. So all I got to do is find the number of math instructors, 7, plus the number of science instructors, 4, add them together, 7 plus 4 is 11, divided by the total number of instructors, which adds up to 19, right? So 11 out of 19. And if you want to, you can divide it and get a decimal or a percent, but fractions in the reduced form are just fine too. Here's another question. This is from homework. Yeah, I think you're going to like this homework. First of all, it's fun. Second of all, it's actually mostly pretty easy, I think. I hope. I select a person at random from all these people that watch these different movie titles. Find the probability that a romance or, that's what you want to circle, the or, a comedy was rented. Well, all I have to do is say how many romances were rented. 310. Plus, how many comedies? 150. Let's see, 310, 410. How about 460 out of a total of, this adds up to 810, I think, if you add up all the different movies. So 460 out of 810, that does reduce, I think, to 46 over 81. I think you've probably done things like this before, because I've taught like pre-algebra in high school and we did stuff like this. Although it will get more interesting because I have some harder, funner stuff, and I'm not an English major, so I can say funner if I want to. All right, mutually exclusive. Let's just give you a picture. This is called a Venn diagram. If event A and event B are mutually exclusive, that just means they can't happen at the same time. Whereas if event A and event B have an overlap, we would say they are not mutually exclusive. And that's why if you count the things in A plus the things in B, you've actually double counted this overlap. And that's why with the probability formula, you have to subtract the overlap because you counted it twice. You still want to count it, but only once, not twice. So that's why you can't just say the number of things in A or B is the number of things in A plus the number of things in B, because again, you would double count. And here's an illustration of that. All right, well, find the probability if I pick a random card that card is a 7 or a club. Well, what you could do is you could say, well, how many 7s are there? There's 4. How many clubs are there? There's 13. 13 plus 4 is 17, right? However, there aren't 17 things here, right? Because the 7 of clubs got counted as one of the 4 7s, but it got counted as one of the 13 clubs. And so I could do 4 7s plus 13 clubs is 17, minus the 1 that got double counted is actually 16. There should be 16 things here out of 52, of course, in a deck. So in probability, or means plus, and means times, kind of, sort of, mostly. That doesn't sound very mathematical. So here it is. Or means plus if events are mutually exclusive, if they don't overlap. But if they do overlap, you have to subtract the overlap because you've double counted it. Whether you have raw numbers that you're counting, like the card problem we just did, or if they give you like the probability of A and the probability of B and they overlap, if you add those probabilities, but they overlap, you get the wrong answer until you subtract the overlap because you don't want to count it twice. You just want to count it once. And means times if events are independent. So we'll get to that. Another thing is the probability of A or B can be calculated by taking the number of things in A plus the number of things in B minus the number of things in A and B that overlap, and then dividing by the total number in the sample space, which is why we just divided by 52 in the deck of cards. Or as I mentioned verbally, the probability of A or B, sometimes they give you information differently in a problem. If they give you the probability of A and the probability of B, you can just add those together. But if those overlap, events A and B, then you have to subtract off the probability of A and B because you counted it twice. You counted it once here, you counted it once here. Yeah, here are two examples. This is from the homework also. Probability a student owns a car is 65%. Probably the probability that a student owns a computer is 82%. Probability that a student owns both is 55%. What is the probability that a randomly selected student owns a car? Or, there's our or, make sure you look for your ors and your ands. This or means plus, right? However, if you took the car probability, 65%, plus the computer probability, 82%, you would get more than 100%, which would break the rules. There would be something really bad that would happen if you did that. However, you wouldn't do that because you see that that 55% actually was counted up here. It also was counted in here. So if you just add those two together, you've double counted. But you can add them together and then subtract 55%. So you only count it once, and that would be 92%. 65 plus 82% minus 55% is 92%. What is the probability that a randomly selected student does not own a car or a computer? Not, right? That's the negation. But an opposite probability is just one minus the other probability. So this was 92%, and the opposite probability then would be 8%. Maybe I'm going too slow. If you look at 14 here. 14 gives you counts. There's 200 male students, 58 play football, 40 play basketball, but 8 play both. What is the probability that a randomly selected male student plays basketball or, look at, there's our or, that means plus football. So you take the 58 plus the 40 minus the 8, because they were counted twice. That's 58 plus 40 minus 8 is 90 out of 200, right? 90 out of 200 play football or basketball. And if 90 out of 200 play football or basketball, that means what, 110 out of 200 plays neither, right? The opposites. Now, I don't think, no, I know actually in the homework there's 3 set problems, but they're really fun if you have a 3 set problem, because if you put an or, like 2 ors, probability of A or B or C, if you have 3 sets with 2 ors and you have a Venn diagram like this, then you have to subtract off the overlaps of A and B, which is like here, if you add them together, and then you have to subtract the overlaps of B and C, and then you have to subtract the overlaps of A and C, but that means you actually subtracted the whole middle, so you have to add it back in. So this is just for fun. Just for fun, that leads us to this formula, which if you want to be a math major and play with this or do some other higher level math, you should go for it because it's super fun. There's fun problems like this. And maybe you want to just pause the video and just play with this for fun because you probably don't have anything better to do. And it'll certainly be edifying. All right, I'll keep going. So or means plus unless there's an overlap. And if there's an overlap, you have to subtract it off, because if you add two things that overlap, you've double counted. That's pretty much what I've said so far, mostly. Now, and means times. So the probability of A and B, you can just take the probability of A times the probability of B. This is pretty good if the events are independent. So that means if A and B actually have nothing to do with each other, at least as it relates to their probabilities. Like if A, the probability of A happening or not happening has nothing to do with B's probability of happening or not happening, then their events are independent. But if A and B are dependent and A happening or not happening affects the probability of B happening or not happening, then this formula reads like this. The probability of A and B equals the probability of A times, this is how you read this, the probability of B given that A already happened. So that's for dependent events, and this will lead us to a conditional probability formula that we'll look at in a few minutes. But let's start with the easy ones. Flipping a coin. If I flip a coin and flip a coin and flip a coin, it has no memory, right? So I flip a coin, and if it turns up heads, the next time I flip it, it doesn't say, well, what just happened? I got to make sure I don't do heads again, right? The probability of getting a heads and getting a heads and getting a heads and getting a heads is just 50% each time. But the probability of getting two heads is 50% or 1/2. And getting another head, remember, and means times. So the probability of getting a head and another head is 1/2 times 1/2, which is 1/4. How about three heads in a row? Heads and heads and heads. 1/2 times 1/2 times 1/2. 1/8. So like there's one chance in 8 that you'll flip a coin 3 times and end up with 3 heads. 4 heads would be 1/2 to the 4th, because it's 1/2 times 1/2 times 1/2 times 1/2, which is 1/16. Excuse me. I need some coffee on a Friday afternoon. That'll help me sleep. How about flipping 10 heads in a row? That's just 1/2 to the 10th power, which is basically not going to happen, right? It's going to shrink to 0. So the thing you need to remember with and is you keep multiplying with and. Every time you attach another event with an and, it forces the next event to happen. But every time you multiply by another probability, which is between 0 and 1, that actually reduces the size of your overall number. So every time you attach an and, it makes something less likely. There's a fallacy associated with that we'll get in a subsequent lesson. Excuse me. Here's a problem from the homework. You're picking 2 cards out of a deck, but actually you're picking one, looking at it, and then sticking it back in the deck and picking a second one. In problem 20 from the assignment, you just pull one out, look at it, and then pick another one. So the second probability in the problem from the homework, you'll pull one card out, and that means there's 51 cards left. And so you have to say, what if I remove that first card? Then what are the chances that what's left has what I'm looking for? But let's just start with this. I pick a card and it's a heart. What's the probability of that? Well, there's actually 13 hearts in a deck. So you see down here, I've got 13 out of 52. That's the probability of picking a heart. I put that heart back in the deck. I pick another card. What's the probability that it's a club? There's 13 clubs out of 52. So look, 13 out of 52 times 13 out of 52, because my operator is and. Now, of course, this is 1/4 times 1/4. So we would get 1/16 when we reduced it. How about this? What's the likelihood of pulling 2 aces? So I pull out an ace, I look at it, I'm like, I just got an ace. The likelihood of getting an ace is 4 out of 52. Oh, that's D. This is D. I was looking down here and I'm like, that's not what I wrote, but D's down here. Yeah, 4 out of 52. I put the ace back in, I pull another card out. The likelihood of it being an ace is the same thing, 4 out of 52. So you could take this and multiply these through and reduce it and get the probability of actually getting 2 aces. Now, of course, if you're going to pull an ace out and not put it back in, the probability of the first card being an ace is 4 out of 52 times the probability of getting a second ace would be 3 out of 51. So 4 out of 52 times 3 out of 51 would be the probability of 2 aces if you were not replacing the card. And of course, if you're not replacing the card, then you don't have independence because the probability changes as you pull out the first card. The next probability changes. But if you're putting the cards back in, then you do have independence because you always have a full deck. So the probability remains the same. So you can go through and play with these a little bit. F is kind of interesting, the probability of 2 of the same card. Well, that means that I could pull a card out and it could be anything. So 52 out of 52 cards would be a success for the first card. Then I stick it back in and the second card that I pull out has to match that first card. And you can see down here, there's actually one card that matches that first card, and it's the one I put back in the deck. So 52 out of 52 is the probability of just pulling out the first card, then I put it back in, and then I have to get that card again. Now, assuming you're shuffling it up and it's actually random. If you push it back in, but you know where it is, and then you pull it out, the odds are in your favor. And that's what magicians do, right? They have clever ways of making it look like they're doing things randomly and not. I have a friend who's one of the best magicians in Oregon. He's just fantastic. Sometimes he's come a number of times to my class and done card tricks, and it is amazing. The guy is just so good. He has these little tricks like forcing a card, where he can hold a stack of cards up, and he'll just have people pick cards, and he's not even looking at the cards, and he knows where they're at, and he can most of the time make you take the card he wants you to take that he knows what it is. So it's pretty cool. He also has these tricks where he takes an unshuffled deck and he does what's called a pharaoh shuffle. He puts the two like half and half exactly together, and then he splits the cards with this special shuffle. He's actually really good at it. He's really smart, but he's also really talented with his hands. He does a pharaoh shuffle, and then from that pharaoh shuffle, he said mathematically, and he doesn't even know how the math works. So sometimes he talks to me and he says, how does the math work on this trick? But he knows that he has like a certain number of pharaoh shuffles that he can do certain kinds of tricks with until it's been shuffled too many times. But if he pharaoh shuffles, then the cards stay kind of in an order. The other thing that's cool is he'll start a trick, and if you don't pick the card that he wants you to pick, he'll just do a different trick. So if he's forcing a card on you and you take the one that he wants you to take, then he can do whatever he wants, right? Because you have the card and he knows it, and he can fiddle around and do all these distractions, and then he'll just come back and tell you what your card is. So he's really good. It's really fun. Sorry, I got on a little tangent. Let's talk about independence versus dependence. So we have two events. We've got the basketball team winning and the probability that it rains. So the likelihood of the basketball team winning is 60%. The likelihood that it rains is 70%. Find the probability of the basketball team winning and, so our operator is and, it raining. Assuming independence, we would just take 60% times 70%. 0.6 times 0.7 is 0.42, 42, right? So we would say there's a 42% chance of both, assuming independence, which is probably pretty fair, unless the basketball team is just not mentally tough, right? If they're not mentally tough, and maybe you know who you are, you're not mentally tough. You're like, it's raining and I just can't play my best because it's raining. No, you're mentally tough. But if it was the football team, we might say, I don't know if we have independence because football's played outside. You know, maybe a team has a particular type of offense that leans toward, say, passing or something, then the ball is wet, the conditions are bad, you don't perform quite as well in the rain. So whether it rains or not would actually change the probability of winning because it would change the game plan and the strengths or weaknesses of the particular team. So, so if you have independence, the problem is easy. You just multiply the probabilities. If you don't have independence, if you have dependence, then you need more information. And that's where you need the conditional probability formula. So we read this, the probability of A given that B is true. So B is the world that you know you live in, and we're looking for the likelihood of A happening in B. But the nice thing about this is it reduces the world because something is true. You already know that. It has already happened. So let's look at this. This is sort of intuitive. I think you could figure this out. What is the probability of a passenger on the Titanic surviving given that they were in first class? All right, so I look at this chart and I'm thinking, this number is probably pretty important to me because these are the survivors in first class, right? But I know that I'm in the category of first class, which means none of second, third, or crew matters to me, at least for this problem. They're probably pretty nice people, so they probably actually do matter. But look, the probability of being in the category surviving and first class, or the number of people in that category, is 203 out of the first classers, which is 325. So this answer is simply 203 divided by 325. So what happens with the conditional probability formula is you're given some information, we're in first class, and that forces you into this particular column, and you look at the total from that column because you know you're in that column. But if you're in that column, you're actually looking for the likelihood of a survivor. So you take survivor and first class divided by first class, and that's your probability. How about this time? Students visit tutoring. We got full-time, part-time students. We got one or fewer, two or three, or four or more times. What's the probability that a student visits tutoring 4 or more times given that they're a full-time student? So the given part actually forces us, in this case, into this row. We don't care about any other row but this row because we know that there are 45 full-time students, and we want to know how many are actually in both categories, 4 or more times, and full-time student, that'd be 8, out of how many are in the world that we know that we live in, which is full-time student. So this is the new sample space, and the numerator in our calculation is the first thing and the second thing. So the probability of A given B is the number of things in A and B divided by the number of things in B. The probability of A given B. So here's a nice picture, I think. I like this. The likelihood of being in A, given that you're in B, is actually this. That's being in A, but knowing that you're also in B, divided by the probability of B. So the likelihood of being in A, given that you're in B, makes the new world B, and the amount of A that's in B, we're just looking for the percentage of A and B out of all of B. So the universe isn't this big pink thing anymore, nor is it the A that's outside of B thing. It is simply the universe is B, and we're looking for the part of B that is A. All right, so how are we going to develop a formula if we have numbers, if we have probabilities? So, by the way, rest in peace, Roy Halladay. We're doing the twin engine airplane problem. If you know anything about baseball, Roy Halladay he pitched a couple of no-hitters, I think. He was an all-star pitcher for the Blue Jays and the Phillies and some other teams. He won the Cy Young Award a few times, but when he retired, they've got this, somebody was taking a picture of this one-man airplane, twin engine airplane, doing these whoop-de-doops. You know, if you're rich enough, you can actually just buy an airplane. So he bought an airplane, and actually he was hyped up on drugs, which is terrible. But he was doing all these crazy things over the Gulf of Mexico, and he did this free fall and just went straight into the Gulf and died, which is really sad. So rest in peace, Roy Halladay. Thanks for the memories. So let's say this, there's 2 engines on a twin engine airplane. Let's suppose that the probability of an engine failing is 1%. That's actually really bad, but let's suppose that. Find the probability that both engines fail, assuming independence. So assuming independence, we would say that would just be the first one fails and the second one fails. 1% times 1% is actually 0.0001. 1 in 10,000. 1 in 10,000. And by the way, I have a couple of friends that are pilots. And if both engines go out on an airplane, even if it's a jet, the crazy thing is they can turn it into a glider and essentially trade altitude for lift. And you actually can land a plane like a glider, which is pretty cool. So, but that actually is just another side story. It's Friday, and you know what I'm like on Fridays? I just start thinking about other stuff. So get your focus. Come on, you got this. Okay. Now, supposing we decided that independence wasn't very reasonable, like if one of the engines goes out, that actually changes the likelihood that the second one goes out also. So suppose we know that the likelihood of both engines failing is 0.001. And we want to know the probability that the second one fails, given that the first has already failed. Well, that's an interesting question because we basically have to take the probability that they both fail. Remember, it's the probability of A and B divided by the probability of B. So we have to take this 0.001 divided by the probability that the first has already failed, which would be 1%. And if you do that, 0.001 divided by 0.01, you actually get 10%. You get 0.1. So that would be bad news, right? Like the likelihood of the second one going out, if the first one has already gone out, is 10%. So good luck with that. But this is a math book problem. It was just made up. So that's what you can do as a math teacher. You can create your own worlds. It's like cartoons, but with numbers. Good times. Here's the formula. The probability of A, given that B is true. Now you've kind of seen this already in this lesson, but I had n's instead of p's. And if you have n's instead of p's, that means you have numbers or counts. But if you have p's, that just means you can do the same thing with probabilities because sometimes the question gives you different information. So the probability of A, given that B has already happened, is the probability of A and B divided by the probability of B. Which means if we have like a whole bunch of information like this, but these are probabilities instead of counts, and this is a car on a used lot. Oh, it says up here, find the probability that the car has a CD player given that the car has an air conditioner. So we would simply say that would be the probability of CD and air conditioner. Where's that? CD and air conditioners right here. It's 0.2 divided by the probability of air conditioner, and air conditioner total has a probability of 0.7. So that calculation would be 0.2 divided by 0.7, which is 2/7. I think that's 0.286, something like that. So you'll see some problems from the homework that look like this. We're sort of winding down. I've got one more fun problem and a couple of just not that interesting problems, but it's on the homework, so make sure that you know how to do it. What you're going to get in some of these problems is they're going to ask you for, in this case, the probability that a student takes calculus given that. So when you see the words given that, you underline and circle them because it means you have a conditional probability. You're looking for something, the likelihood of a student taking calculus, but we know that that student is on the dean's list. So look at what I wrote. The probability of calculus given that dean's list equals the probability of calculus and dean's list, which we have up there, that's 0.042, divided by the probability of dean's list, which we also have that's 0.21. So 0.042 divided by 0.21 equals 20%. You could do the same thing down here with question 25. So I think those are pretty straightforward. And one last thing here. We're going to use the property of opposite probabilities, which is pretty cool. And I think it's pretty obvious. The likelihood that it rains, if it's 70%, the likelihood that it does not rain is 30%. They have to add up. Opposite probabilities have to add up to 1. That's intuitive. So the probability of not A is 1 minus the probability of A. And I just want to end with the birthday problem. It's a paradox, which is just like, it totally doesn't seem like this would be true, but it is, and it can be proven mathematically. So this is a famous math problem that will blow your mind. How many people need to be in a room in order to have a probability greater than 1/2, more likely than not, that at least 2 people share the same birthday? And by that birthday, we would say the same day of the year. Not necessarily the same year, but the same day of the year. So it turns out that this is actually a very complex problem and can be much more easily solved by finding the opposite probability. So we want to know the probability that at least 2 people share the same birthday. And our strategy is to do 1 minus the probability that they don't. So there's some people in the room and we're wondering, what's 1 minus the probability that they don't have the same birthday? And by the way, you might think, well, how many people would there need to be in a room for there to be a 100% likelihood that 2 people had the same birthday? Now, assuming that February 29th is a possible birthday, there's actually 366 birthdays. So there'd actually have to be 367 people in a room to guarantee 100% that 2 people had the same birthday. And the crazy thing is, the likelihood that 2 people have the same birthday, if there are 23 people in a room, is bigger than 50%. But it takes 367 people in the room to get to 100%. So it's not a linear relationship at all. And I'll show you how it's calculated. You kind of look at the problem as though there were 2 people in a room. So 1 minus the probability that the 2 people in a room don't have the same birthday. Essentially what you do is you say, you check the first person's birthday, and they could say anything they want, kind of like picking that first card in the problem we just did. But there's 365 out of 365 days for the first person to not match the other person's birthday. But then the second person, there's only 364 out of 365 days that would successfully not match the first person's birthday. And so you do 1 minus that, you get a number. Well, if there's 3 people, then we have to check a third person. And once we check the first 2 people, then that third person will have 363 days. By the way, this is not assuming the leap year in this problem. 363 days out of 365. And so you can see the pattern that we just keep checking the next person, but we've checked a previous person, and now their birthday is not a candidate for the next person because we're looking for the probability that they don't have the same birthday. And it turns out, yeah, with 22 people, I guess, I was thinking it was 23. 22 people, there's better than a 50% chance that 2 people have a common birthday. And by the time you get to 40 people, there's a 90% chance. But again, it takes 360, well, technically 7, but in this way of looking at it, 366 people to have a 100% chance. Now, you won't have to do this on the assignment. This is just a cool problem. And I thought it would be nice to end the week with a cool problem. You can also see this is not a linear relationship. These are a number of people in a room. And this is the probability that 2 people have the same birthday. Hits 50% at about 23. And then it starts flattening out. And you have to actually, to get to 1, you have to go all the way to 366. So crazy times. Problem set CT3 is a worksheet. It's up for you. I hope you had a good time. I know I did. And I'll see you after this weekend. Bye-bye.